Hello, everyone. Now, when I was in school, my teachers used to complain to my parents that I don't come to the school. And they were right. I was spending most of my time in chess tournaments, at chess clubs. That was what I was doing. But when, by the age of 17, I didn't become a grandmaster, the highest level in chess, I figured out I'm too old to ever have any realistic chance at becoming world chess champion. So what did I do? In Israel, we have a saying, if you don't get accepted to become a pilot, you go to anti-aircraft missile division. If I don't fly, nobody flies. So I said, I will develop a chess program that would defeat the world champion. That's how my passion for AI started, and it has been at the center of my life for the past 20 years. AI, artificial intelligence, is a very wide umbrella term. Anything that exhibits intelligence is artificial intelligence. It doesn't have to do any learning. IBM's Deep Blue, who defeated Garry Kasparov in chess in 1997, that was a great example of AI without any kind of learning. It was just one giant calculator. Under AI, we have a certain subdomain, which is machine learning. The difference being that here the machine learns by itself rather than being explicitly programmed. Within machine learning, we have many different subdomains. One of them happens to be neural networks, or deep neural networks, also known as deep learning. Until a few years ago, neural networks was considered a completely refuted field of research that no serious researcher would get into that. That's why I got into that. But there is a big conceptual difference between deep learning and these other forms of traditional machine learning. Let's see what's the difference and how it would apply to cybersecurity. Let's take as an example the problem of face recognition. Now, many of you would recognize the face here. Let's first use traditional machine learning to do that. In traditional machine learning, we cannot feed the raw data, in this case the raw pixel values, directly into the machine learning module. We cannot do that. So what can we do? What we must do instead, bring a domain expert, in this case it would be an image processing expert. They would analyze the problem and tell us what are the most important properties, the features here. A phase known as feature extraction. For example, here the most important features would be, let's say, distance between pupils, distance between nose and mouth, proportions of the face, texture, color, etc. Thus, we convert the raw data into a vector of features and then feed that into our machine learning module. Wherever we use traditional machine learning, these are the steps. For cybersecurity, take an executable file, decide what are the important function calls, vector of features, and then machine learning module. But there are two big problems doing this kind of machine learning. First, by converting the rich raw data, millions of pixels in this example, into a small list of features, as good as they may be, we're throwing away most of the data that we have. We're looking just partial data. But secondly, and even more importantly, we humans, even the best experts amongst us, we're terrible at doing feature extraction. We're not good at articulating the features, the important properties. Let's use a much easier intuitive example to explain that. Now, everyone here, I guess, is a world-grade expert in detecting cats and dogs in images. I see a few experts over there. If I show you a picture of a cat or a dog, in a few milliseconds you will tell me if it's a cat or a dog, and you will have near 100% accuracy. So, who can explain to me what is the difference between a cat and a dog? Well, I will not waste your time. That's why I have students at university. What people usually say, well, a dog is bigger. Yeah, that's maybe a good feature. A dog is usually on the ground, a cat is on your table making a mess with your papers. Tell that to my dog. This is how I found him the other day on my desk. And he's smaller than a cat. He thinks he's a cat. He may very well be a cat. Or at some point, after I waste my students' time too much, they say, oh, there's a difference. The pupils are different. The pupils of dog are more circular, those of the cat are more elliptic. Finally, a good feature. You recognize a cat and dog here, I hope. And now, even though you see the picture, you still have difficulty explaining that. This thing about our brain, we immediately learn something. We're good at that, but we're not good at the process of converting that knowledge to features, articulating those things. So what's great about deep learning? It's the first and currently the only subfield within machine learning that can skip feature extraction. Using deep neural networks, we would not do any feature extraction. We would just feed raw pixel values directly into our deep neural network. And by creating a deep hierarchy of features that it learns by itself, it will do much, much better. And the results obtained by deep learning in the past few years have been the greatest leap in performance in the history of artificial intelligence. For many kind of benchmarks where we were used to seeing 0.5%, 1% improvement a year, suddenly we see 20, 30% improvement. In vision, for many benchmarks which we have 70% accuracy, now we stand at 97, 98% accuracy, sometimes even surpassing the human accuracy, the greatest revolution we observed. So if the results are so good, and they are amazing, for vision, for speech, for text, why not use it for cybersecurity, to detect the latest malware? We've got a few problems here. The screen is okay, it's working fine. I bet you're seeing random data here. This is not random. This is how it looks if you take an executable file, and you look at some parts of it, the raw bytes, as if they were an image. It looks random to all of us here, but it's full of patterns. The patterns are just not local. We don't see local correlations like in images, like in speech. So any kind of neural net that uses local correlations cannot be applied here. And we have additional challenges. For example, in addition to the fact that we cannot use standard deep learning models, the input varies substantially in size. What if we have two images of different sizes? We just resize them to a predetermined fixed size. What if we have a file which is 100 kilobyte, 100 megabyte, or 100 gigabyte? We cannot just resize that. And the file formats are different. You can be infected by executable file, PDF file, Office file, different file formats. So these are really challenging problems that we cannot apply traditional standard deep learning models to them. So what can we do? Many people look at deep learning like a lamb, and you just rub the lamb. The genie comes out the lamb, say, "Oh, my master, what's your wish? Give me your training data, I will feed them into TensorFlow, and then here is your model, it will work." Well, it's not really like that. Let's see what we need to make it work anyway. First of all, we need lots of data, actually huge amount of data. In this case, cybersecurity, luckily, we have every day 300,000 data. We can quickly grow data sets of hundreds of millions of malicious and legitimate files. We're good at that. We need deep learning experts. Still a hard resource to find the best deep learning people, those who know the field intimately enough to be able to modify the algorithms for this field. Let's say we covered in that as well. And the easiest part, we need a deep learning framework, a software library that allows us to write deep learning models, to program them, and then run it. This is the easiest thing, right? Let's dwell on this for a moment. So first of all, the good thing about the deep learning frameworks. Until a few years ago, if you wanted to write a deep neural network, you would need to write it low level, usually in NVIDIA's CUDA code, the closest to the hardware, because today for training deep learning, GPU is the only relevant hardware. And if you look at the universe of people who have high-level research expertise, and those who know low-level programming, these two worlds really don't intersect. But today, you don't need to do any low-level programming. You can use any of these great software libraries, TensorFlow by Google, PyTorch, Keras, all the others. You will just write your high-level code, and it will automatically be translated to low-level code, and it would work great. This is an amazing breakthrough. This is the good news. But besides the good, we also have the bad. These frameworks are developed for research, not productization. They have many limitations for productization. They are mostly deployed on cloud due to the many dependencies that they have, and that's problematic. You put it on the cloud because of the specific hardware that they need, lots of memory that they need, even for inference, after you train them, for continuous prediction. Sometimes you would like immediate reaction. By the time I send your suspicious file to the cloud and the result comes back, half your network is infected. Sometimes you don't have continuous connection to the cloud. The costs are too high. And it's very challenging to deploy it on edge devices, on your mobile laptop, desktop, because of the need for huge amount of processing power, huge amount of memory that typically you don't have on your edge devices. These are some of the big challenges. That's the bad. What comes after the good and the bad? The ugly. The ugly thing about these deep learning frameworks is that expose high-level building blocks. You can imagine, for example, TensorFlow, PyTorch, or all the frameworks, they give you Lego bricks, building blocks, that you can then put them together in infinite ingenious ways and obtain amazing results for vision, for speech, for text. But for some problems, you must modify the core algorithms to make inherent modifications inside these Lego bricks. And if you need to do that, you're completely out of luck. You cannot do that with these frameworks. This is not a speculation. This is a definite future. Every technology will be used for good and for bad. And to prevent this scary future, we must accelerate the pace of adoption to bring amazing results we see in AI from research to productization. What do we need for that? What are the main things? Not only for cyber, but general for deep learning. My firm belief is that to bring the amazing results of deep learning we see in research to mass-scale productization, we must improve edge deployment, edge inference. Exactly like Young-Sun mentioned before. All the devices that you have, all the IoTs, drones, cameras, mobile, laptop, we need to implement deep learning and put it on inference on those kind of devices. What do we need to do that? Not just for cybersecurity, by the way, for vision, speech, text, all these kind of amazing results. For healthcare, that's one of the most important things we need to bring it on edge devices for inference. We need two main components. First of all, we need faster and more efficient processing. Not necessarily hardware. We're assuming that for better, faster, more efficient processing, we need faster hardware. Not necessarily. There may be an algorithmic solution to this as well, not necessarily hardware. If we look at our brain, for example, we're operating at 20 watts. A single GPU is operating at over 300 watts. What does it mean? It means that most probably there are more efficient versions of the algorithms we're using to be able to deploy it on slower hardware as well. How about memory consumption? Today's neural networks are based on dense representations. A dense multidimensional matrix called tensor. That's why the name TensorFlow comes from. It's all dense. Our brain is extremely sparse. In our neocortex, the cognitive part of the brain, we have 16 billion neurons. Each one of them is connected to only about 10,000 on average. It's very compact and efficient. Maybe we can make deep learning algorithms much more compact and efficient, such that you could deploy them. Well, I would like to show you the most important deep learning paper ever published. Learning representations by backpropagating errors. Every deep learning algorithm you use, for vision, for speech, for text, for cybersecurity, you're using this algorithm, the backpropagation algorithm, for training the neural net, for gradually updating the synapses of the neural net until it trains. And this paper was co-authored by Geoffrey Hinton. For the past 30 years, he relentlessly focused on neural nets. His entire life was devoted to the research of neural networks, where nearly everyone was convinced that it's a futile attempt and nothing good will come out of neural networks. And he's, by the way, the reason why I got into neural networks. I really believed in what he believed in. And he's a co-author of this most important paper. When do you think he wrote this paper? And by the way, he's also one of the main figures behind the current renaissance of neural networks, the current deep learning. When did he write it? 2 years ago? 5 years ago? 3 years ago? 32 years ago, 1986. The most important deep learning algorithm, which every deep learning today is using, was written 32 years ago. Is it possible that nobody can improve upon this algorithm? We cannot make it more efficient? Let's see what Geoffrey himself thinks about that. When asked, he said, "My view is throw it all away and start again." Maybe not throw it all away and start again, but at least we must find some major improvements on top of it. At the beginning, I told you about my passion 20 years ago. It was chess and computer chess. This is my passion today. I spend my time focusing on this kind of core research to making neural networks much sparser, much more compact, to be able to, instead of hundreds of megabytes of memory, use tens of megabytes of memory. So that instead of having large dedicated hardware for inference, we can put them on edge devices and get closer to the vision that in a few years from now, we could employ neural networks on each and every device in the world. Thank you very much.